purpose. There are some days when you come in, there will be a quiz like this, a mini quiz that we'll do together. Some days there may be, take out a piece of paper and do this on your own and we'll turn it in. And then I will still reserve the right to not count the grade. Part of what I'm going to start doing now is more actively using quizzing as a teaching technique, not as an assessment technique. So what does that mean? You, like we did with the polyatomic ions, you preparing for quizzes and coming in here and needing to remember things, actively stretching yourself to remember things is actually you learning things. Whether you did or didn't know all these blanks before, you've seen them again in a different way, and your mind is making different neural connections to that information. Okay? So for those of you that knew it, you know it a little bit better now. For those of you that didn't know it before, you know it some now. And we're using a quiz like this as a teaching technique, not as a way for me to give you a grade. It's like just one of the many things, like reading, like tutoring, like quizzing now is an active quizzing regime for the class. However, if you don't take the quizzes seriously, like it's like, that never counts, we do this every day, well, then we'll start collecting them and using the grades too. Okay? So get a little bit of pressure, because frankly, you don't really learn. Nobody really learns unless there's some pressure of some kind for you to learn. Now, there are folks who love to learn. And that's one of the common rubs between teachers and students, is students want to know, but why do I have to learn this? Tell me now exactly how I'm going to use this in the future, because unless you can prove to me that I can use it somehow, I don't value it at all. And teachers tend to be more on the side of learning is its own reward. You learn because you get to learn. And you have a sense of value and satisfaction because you've learned, not because you can take it and have somebody pay you, $10 an hour to do it. And you become a more well-rounded person. You may never know exactly how you're going to use stoichiometry in the future, but being able to sit down and figure out a problem using logic, knowing that if I apply myself to this problem, I will eventually be able to solve it. Now, there are some folks in here that I try not to read too much into it, but I can see in your eyes, there's some folks in here that sit there and go, you know what, Mr. Baker? You can throw me something. I may not know how to do it, but I'll figure it out. And if for no other reason than I enjoy figuring stuff out, I'm going to figure it out. Nobody has to pay me to do it. No parent's going to punish me if I don't do it. That's my bent. Throw me a problem, I'll solve it. Why? Because I get satisfaction out of solving puzzles and problems. There's other people who in here are saying, you know what, dude, I'm trying to avoid as much work as possible. I want to get it done as quickly as possible. And the only thing I'm trying to avoid is looking like an idiot in front of my peers or looking bad in front of my parents because they've got some expectation of me to go off to some like Ivy League school. And the only way I can keep that hope alive for them is if I don't get less than a B in this class. Well, you know what? If your attitude is, I'll do as little as quickly as possible, just enough to get by, you probably should kind of start thinking more like JCTC or something for school, okay? If that's what you need to do. Because more of it is about your attitude about learning than it is about the subject you're learning. If you put the right attitude in a person, no matter what the course of study is, they're going to do okay in it. They may not excel, it may not be their area of expertise, but they'll apply themselves in it. And really, I've mentioned this to you before, this chemistry class is as much about you learning how to learn as it is about chemistry. As a matter of fact, it's more about learning how to learn. We're just using chemistry as a way to help you learn how to learn. So, I had to read these 2 books over the weekend, and they're talking about things like flashcards and quizzing and drilling and recognizing that teachers stop trying to make class so easy for your students because the struggle that they have is actually them learning. I thought of several worksheets that I could come up with, several templates that I could come up with, ways that I could help you. For example, I drew this whole decision matrix on, here's a molecule. Is it ionic or covalent? What dissolves it? How is it bonded? Has all these different questions, and you start at one end, you answer all the questions, and at the other end, you're done. It's all solved. And part of what the book said to me was, why are you doing that for your students? Shouldn't they be saying, hey, wait a minute, Mr. Baker, I see trends. We do the same kind of problem over and over and over again. So I sat down and I said, hey, let me write down what happens on every kind of problem like this, and let me put it in order, and let me show you my decision-making matrix. Now I've figured out a way that I'm going to solve these kind of problems. Awesome. Okay? But there also is this aspect of, I as a teacher, and this isn't an ego thing, just the phrases they use, I have a more expert understanding of this information. So the way this information is organized in my mind is different than the way it's organized in the mind of a novice. So expert-novice kind of relationship. I'm an expert, you guys are novices at this, right? So the way the information is organized in my mind is different than the way that it is in your mind if it's there. And it's getting there, right? My job is to help get it there. But not only to get it in there, but to help you organize it in some useful way. So there may be times when I'm going to say, this is how I want you to think about this. And what I'm trying to do is give you a way of understanding it that's similar to the way that I understand it, or hopefully the way, a better way for both of us to come to understand it. Because it's about think of your mind as a bunch of index cards. And if your mind was a bunch of index cards that looked like your room right now, how well would you do on an exam? Just think about that. I don't know how your rooms look right now. Did anybody make their bed when they left? Anybody vacuum their room before they left their room? Did anybody, what does your room look like? And think about that. If your brain was your room and your ideas and information were index cards, would they be at least all together in a pile in a corner? Would they be all facing the right way, upright and forward? Would they be organized and cataloged alphabetically or by subject matter? So you all have your minds. You all have that ability. It's about having the information. Some of it involves rote memorization. Like I told you, polyatomic ions, just have to memorize them. Sorry, there's no trick. You just have to memorize them. Now, how do you organize them? And some of you did that in here. The little ditties you came up with. Remember we showed some people did rap songs. You guys had this phoneme thing. How'd you do it? Okay. So you came with a mnemonic device to learn that. I could have given you the rap songs on YouTube and said, go to this one and memorize this rap song, right? But by you taking the time to come up with some way to learn it and to memorize it on your own, you increased the way your mind organizes, and you perfected the way your mind organizes those index cards of information. So, things like that. What do you need to do to learn? Also, got a lot of time this weekend saying all this idea about learning styles, auditory, kinesthetic, visual. It's bunk. They exist in your preference, but actually, learning to learn outside your preferred style causes you to think harder, which causes you to learn better. So they encourage teachers not to placate to the learning styles of each individual student. If you think you're a visual learner, that doesn't mean, okay, just go in the corner and read your book, and I'll talk to the people who are auditory or kinesthetic. We're all going to have to do it together. If you're not a visual learner, then reading the book is a good way for you to learn because you've got to work harder to learn it. If something is easy, anybody could do it. And if anybody could do it, what's our economy? How's it going to demand people to do that? How many really high-paying jobs are there out there that anybody can do? That's legal. I have to give that caveat to some of you, okay? That's legal. I assume most of you would work along that understanding anyway. All right, view to the camera so I can know where all this pontificating ended. Let's turn together around page 221. Page 221, chemical reactions and chemical equations. You did see a taste of this on the last module exam when you had the question that said, given the following reaction, it gave you this molecule and this molecule react to produce a third molecule and a fourth molecule. Remember that question? And I said, and I actually drew the equation out for you on the test and said, don't worry about what's happening here, just give me the formulas for the 4 different molecules that you see. That was what was on the module exam. We're going to start now actually using chemical equations and hopefully understanding what's being represented, what they mean when you see a chemical equation. Now this is a section in the second edition where you would learn about homonuclear diatomics. So you guys are well past that. I don't need to go into my notes on that stuff. But one thing you do need to understand is when we're talking about chemical equations, your rules about homonuclear diatomics go away. What I mean by that is, when you have an element in its elemental form in a chemical equation, it's going to follow the rule of homonuclear diatomics. For example, we're going to talk about forming carbon dioxide. We're going to have carbon, and we're going to add to that oxygen. When we add oxygen to carbon, hopefully you see that I'm trying to approximate an elemental form here. Oxygen isn't combined with anything else. It's oxygen all alone. And when oxygen is all alone, we know that it is a homonuclear diatomic, so we're not going to find oxygen alone, single atoms of oxygen in a room or in a space. They're going to automatically combine to form homonuclear diatomics, so we would expect to find carbon and O2 molecules. So carbon atoms and oxygen molecules, because it's a homonuclear diatomic. Carbon and oxygen are going to react. We'll get into what it means to react in a moment, but carbon and oxygen react to form carbon dioxide. Okay? Now, carbon. If I ask you right now, is carbon a solid, liquid, or gas? Your response would be, yes, I need more information. And if I were to say to you, is carbon do we normally find carbon? When I say normal, I mean at 1 atmosphere at standard temperature. Do we normally find carbon as a solid, liquid, or gas? Think of it as a solid piece of coal. Coal is usually the mental image of what is carbon? A piece of coal. We normally find carbon as a solid. So now we're going to start adding this idea of phase symbols. It's okay for me to say carbon and oxygen react to produce carbon dioxide. That's correct. It's more correct for me to tell you solid carbon reacts with oxygen. Normally, how do we encounter oxygen? In what phase? It's gas. So solid carbon reacts with gaseous oxygen to produce carbon dioxide. And again, at standard temperature pressure, we encounter carbon dioxide as what phase? It's a gas. You know, look at your partner and breathe out on them real hard. Okay, that's carbon dioxide, right? If it was solid, that's not what you're getting, okay? That's not the carbon dioxide that hits you, okay? You breathe in oxygen and nitrogen and carbon dioxide and a bunch of other stuff. But we breathe in all these gases, and our body, as it takes in this oxygen, our body is a big engine that's burning fuels that have carbon chains in them. And so we breathe in oxygen, and we breathe out less oxygen, and we breathe out more carbon dioxide than we breathed in. What's happening? In our bodies, we are combining carbon and oxygen to form carbon dioxide. Okay. Our body is combusting, burning. This is combustion right here. This is a form of combustion. Burning coal. If I burn a lump of coal, what do I need to burn something? Fuel. Remember the fire triangle? I need fuel, oxygen, and heat or energy. So if I have carbon and oxygen, I've got fuel, oxygen, I add heat, I get a reaction, and I form carbon dioxide. Now, all of the chemical reactions, this is a chemical equation that I have on the board. A chemical reaction is reactants, and reactants for now are going to be always on the left-hand side of the arrow. Our reactants are on the left-hand side. Okay? So what are the things that react together to form something else? The reactants are left-hand side. The reactants react, to form products. Reactants react to produce products. As you look at the board, left to right, the standard notation is going to be reactants on the left, arrow pointing to the right, products. These take us to this. The reactants take us to the products. The reactants become the products. The reactants are transposed, transformed, reconfigured to become the products. Remember, We've got a couple things going on here. We've got conservation of mass, which tells us what? We're not creating or destroying anything, right? It's a closed system. So what we're saying is all this is going to be happening in a closed, like aquarium with a lid on it, okay? Nothing new's coming in. Nothing's allowed to escape. If everything that we have to start with is captured, well, wait a minute, it changes into something else. Yeah, but here's the thing. Whatever mass we have to start with, we have the same mass when we end. In this case, we've got a solid. At the end, we have no solids. Everything becomes a gas. But guess what? The gas of the carbon dioxide at the end of this reaction is the same mass as the combination of the mass of the carbon and the mass of the oxygen before they react. So no mass is lost. Now, hopefully before, from the law of mass conservation, or conservation of mass, whichever way you say it, we've learned that point, right? That makes sense to us. We start with a certain mass, and we do something with it, but we end with a certain mass, because all we've really done in a reaction is swap things around, move things around. If, for example, I have this little Lego structure, right? And it's got this long red, these 4 yellows, and these 2 small blues. And I gave it to somebody that had some kind of aesthetic ability. Not. Okay. I go, okay, make something else out of it. Go ahead. Just make something else. Okay. You made something else out of it? Did you lose anything? Did you get anything else? No. Is it the same as it was? It's not the same structure, right? It's the same building blocks, but it looks different now. But we haven't added. We still have the 1 red, the 4 yellows, and the 2 blues. We haven't added or taken anything away, but it's not like it was, right? Let's go ahead, come up with something else. Okay. Did you add anything? Did you take anything away? But it's not the same, is it? But it's the same. Everything he had to start with, we ended with. It doesn't look like it did before. And Ray? Here, go ahead and make 2 things out of that. 2 things. Now we've taken this structure we had, and we're creating something different. Don't take too long at it, but yeah. Just do what you can do. Okay? That'll work. So, wait, before I take these, did you add anything? No. Did you take anything away? No. No, you didn't. You didn't have an extra Lego in your pocket that you added, right? So we now have 2 things, but do you see that I have exactly the same amount of stuff that I started with? Okay? And if these 2 things were tight together, what phase would they be probably? Solids. And if they had a lot of space, what would they be? Gas, because at the molecular level, they don't know what phase they are. They just, phase is all how they are related to their neighbor, right? So the point is, whatever we have to start with, we have the same to end with. If you think of, and this is where we get back to Dalton's law, right? Dalton's talking about his chemistry laws, and he said, and we say that he's not technically accurate when he says that the atom is the smallest individual building block of matter, because we know we can remove electrons, we know we can remove neutrons or add neutrons, right? So it's not perfectly indivisible, but for most purposes, the smallest thing we have is the atom. And so I've got certain atoms, and what I'm doing is I'm taking these atoms that I start with, and I'm changing their structures, but in the end, I have all the exact same atoms I started with. They're just put together differently. Okay? Does that make sense? We're not adding any Legos. We're not taking away any Legos. We're just manipulating how they look. In a chemical reaction, we're not adding any atoms. We're not losing any atoms. All we're doing is reconfiguring the atoms to form different structures, which come out as different molecules in the end. So, there's one other phase, again, It's on the table on page 223. Table 6.1, it's not represented up here, or two of them that aren't represented up here, which we have gone over. You've got solid, gases. If you put an L, it means it's liquid, in liquid format, or liquid form. And then there's a fourth one, which is aqueous. So liquid is just parentheses L, which sometimes looks like a 1, so I'll put a little tail on it or something like that to say L. And then AQ, aqueous, means it's in water. Aqua. So salt water would be NaCl aqueous, salt water. NaCl in water, NaCl aqueous. Okay? So it's not always vital information, but it is helpful. Because if I, in this case up here, I can say, okay, when I do this reaction, I'm going to have a block of carbon. How do I know it's a block? Because it's solid. And I'm going to pipe into that some gaseous oxygen. Oh, and then I'm going to light a match. Right? And when I'm done, I'm going to have carbon dioxide. The magic flash. That energy that I'm adding does something. And we'll talk about what it does in just a moment here. But, again, for fun, let's look at another reaction. Again, reactants to form products. We talk about this on page 224, talking about combustion of methane. The combustion of methane. That methane, formula CH4, we encounter that as a gas, and oxygen, encounter that as a gas, reacts to produce carbon dioxide gas and water vapor, H2O gas. I mentioned this before, that this is a classic combustion reaction. We're going to learn different types of reactions very soon, but this is a classic combustion reaction. I have a fuel, reacts with oxygen to produce carbon dioxide and water. I sometimes refer to these as a CHO reaction, or CHO molecules. I did that before in here. I thought that, CHO, yeah, but trust me, it's going to be helpful over and over again. Look at carbon, hydrogen. The fuel is normally a carbon, hydrogen, or sometimes a carbon, hydrogen, oxygen chain molecule. This fuel plus oxygen produces carbon dioxide and water vapor. The standard products. In your car, you're burning gasoline. In the engine, you're mixing it with oxygen. And you're adding a spark, which is the energy, to cause the reaction that converts gaseous and gaseous into the exhaust, carbon dioxide, and water vapor. We said before, the water that drips out your tailpipe, some of it is from condensation, but most of it is a product of reaction. It's a product of the burning fuel in your engine. That's where that water comes from. It's water that's formed from the hydrogen in the fuel chain and the oxygen in the air. Produces the water as part of the product. Now, if we take this same structure that I had here before, see, I need CH4, so we'll say that it's here. The red's the carbon, the yellows are the hydrogen, right? There's a CH4 molecule. Let's pretend. CH4. I need 2 oxygens. There's my O2 molecule, right? All right. I need to take these blocks and make carbon dioxide and water. Well, an oxygen is a blue, so a water is a blue and 2 yellows. There's H2O. And then I need a carbon. Wait a minute. It doesn't work. I can form the H2O, but I have 2 extra hydrogens because I don't need them in the CO2, and I'm lacking an oxygen. This is just a CO, not a CO2, with 2 extra hydrogens. So how can I actually, if I say that this reaction is correct, how come I can't make all the products? And the reason you can't make all the products is the reaction isn't balanced yet. In order for the reaction to be accurate, to be fully correct, not only do the reactants and products need to be identified correctly, but you also have to have the appropriate amount of them. And this is where I say we need to create the perfect recipe for this reaction. When I say perfect recipe, before we've used baking recipes as kind of an analogy, how to do it. And this is where a baking recipe and a chemistry recipe really don't match perfectly. The analogy kind of goes too far. Because if we were to make a cake, and I said, okay, the basic ingredients, I know there's more, but if I said, okay, if you have flour and eggs and you combine them to make cupcakes, okay, and there's a recipe for that, and you have a certain recipe that you use. We just came off a holiday, we're going into other holidays. It's food holidays, right? Lots of cooking. There's certain recipes, grandma's chocolate chip cookies or whatever, and somebody tries to make the cookies, goes, it's just not the same as grandma's. How did she do it? It's close, but it's not the same. And so you do all these different investigations. If, for example, it took a cup of flour and 2 eggs, and you put a 3rd egg in, your cupcakes are still going to come out, right? But they're going to be off. They're not going to taste right. In chemistry, if you put in the wrong mix of ingredients, it kind of rejects it. Let's say you did a recipe and it worked like chemistry. You're supposed to put 2 eggs in, you put 3 eggs in. When you're done, guess what you would have? Cupcakes and an extra egg. It would kind of reject whatever it didn't need. It would leave it outside. It wouldn't just take it and use it and go, okay, whatever, I'll make whatever. That's where a baking recipe says, I'll take everything and just kind of make one thing out of all of it. And it may not be what you're looking for, but it'll be something. In chemistry, it's like, no, we're making carbon dioxide and water, and if you've got too much or too little, we just won't be able to make as much, or we'll make more, but you know what? There's going to be leftovers. Let's get into this idea of the chemical reaction and balancing it. If I'm going to say to you, whatever we have on the left side, we have to have on the right side. In terms of the individual atom counts, the individual atoms. This statement up here, in general, is true. Yes, methane reacts with oxygen to produce carbon dioxide and water. That statement is true. But it's not completely correct. I mean, it's not completely, it's not all the information you need, or not the perfect recipe, the balanced chemical equation. Now, we've added more information. Gaseous methane and gaseous oxygen reacts to produce gaseous carbon dioxide and gaseous water vapor, right? It's redundant, water vapor, gaseous, but water vapor. That's more information, but it still doesn't work out. What I need to do is make sure that I've got the same number of every single element on both sides of the equation. So this statement is generally true, but it's not technically fully accurate. Okay? What I need to do is look at every single element on the left and make sure that I've got exactly the same number on the right. And here's how we're going to do that. This is very, very important. So if you're nodding off at all and you need to stand up, please do it. This is critical stuff, because this is the language we're learning so that we can eventually get to stoichiometry, which is chemistry. Okay, so again, we're still just learning the language so we can talk about it. Think about it that way. The first half of the class is just to learn the language so we can actually talk about chemistry. We're almost there. And it's important. Anybody see the movie Arrival? No? It's a cerebral, intellectual sci-fi movie, so most of you wouldn't get it anyway. So don't worry about it. Anyway, it was meant to be funny, but okay, let's look on the left-hand side of the equation. What elements do you see? Not molecules. What elements do you see? And what I do, technique-wise, again, this is where the expert talking to the novice. This is what I do. If something works better for you, that's fine, but I think this will work for you, is I start on the left and I just read from left to right, and I write down every element that I see. So starting from left to right, what's the first element you're going to see? Carbon, right. So I have carbons. What's next? Hydrogens and oxygens. Joe. Okay? Okay. Now, that's all I have. Those are everything that's on the left-hand side. All of the reactants, I can build all of them. If I've got carbon, hydrogen, and oxygen, I can build all of those molecules. Agree? Now, how many of each of these do I have? And what I'm going to do is, right, products and reactants. So I'm going to look at products, or excuse me, we do it backwards. Reactants and products. I'm going to look at the reactants, and then I'm going to consider the products. So I'm forming a little grid right here. I won't always draw these lines, but for right now, it might help. Okay, so I form this little grid pattern of each of those elements and each of those places, reactants and products. Now, hopefully you agree with me. If all I have as reactants are carbon, hydrogen, and oxygen, then everything I make has to be able to be made out of carbon, hydrogen, and oxygen. I can't suddenly have, like, astatine show up. Like, where'd you come from? You can't be in the products if you're not in the reactants. So now we know everything is going to be made up of carbons, hydrogens, and oxygens. Why? Because that's all we have in the reactants. Oh, if we didn't know what the reactants were and all we had were the products, we would look and say, okay, it's carbons, oxygens, hydrogens, oxygens. Everything in the reactants has to be carbon, hydrogen, and oxygen. Why? Because that's all I have in the products. See, it works both ways. I can't get something that I didn't start with, and everything I start with I have to have at the end. Now, how many carbons do I have in the reactant side? Again, I go left to right. Carbon, how many do I have? Here's what I want you to do. I have one set of one, right? Because there's one carbon in this whole molecule, right? I have one set of one. You'll see why in a minute. Next, hydrogens, going from left to right. I have one set of four. And again, when I do this, carbon, there, nowhere else. Hydrogen, there, nowhere else. And then in oxygen, left to right, only there. It's one set of two. Okay? So total, carbons on the left for the reactant side, I have one, hydrogens four, oxygens two. 1, 4, 2. 1, 4, 2. Now on the product side. Carbons. Looking from left to right. I have one set of one. Anything else? No. One set of one. So with regard to carbon, that's a balanced reaction with regard to carbon. Why? I have one on the left and I have one on the right. I have one reactant carbon. I've got one product carbon. Carbon's good. But hydrogen. Left to right. Here and only there. I have one set of two. I started with 4 hydrogens and I end with 2 hydrogens. It's not balanced. I need to get 2 more hydrogens on the left-hand side or on the right-hand side, right? Because looking at this, I haven't used 2 of them. 2 of them are out there free-floating. It would be like if I did this. Oh, okay, yeah, now I've got one set of 2, and I've got 2 sets of 2, I've got 4. But that's not what we're producing. We don't have elemental hydrogen as a product. Now let's look at oxygen real quick. Oxygen from left to right. One set of 2. And one set of 1. For a total of 3. All right. This is where we get into coefficients. I told you before that we can't play God and create different molecules. I'm going to tell you right now, the products are going to be carbon dioxide and water. We can't decide, no, I want it to be hydronium, H3O. I just arbitrarily decided because I'm God. Maybe that's the way you view yourself in your personal life, but here in chemistry, doesn't work. God said methane and oxygen produce carbon dioxide and water. Okay, well, I don't have the authority to mess up with what the reaction produces, but what I can do is come to recognize that it's not always a 1 and 1 produces 1 and 1. Sometimes there's other multiples that are taking place here. For right now, let's just look to the right-hand side, look at the carbon dioxide and water and say, wait, okay, I need to get 2 more hydrogens. Where do hydrogens show up? Oh, they only show up in that one place right there. How can I possibly go from 2 to 4 hydrogens by modifying this molecule without changing any of its elements or any of its subscripts? I just add a coefficient of 2. Now I've added a coefficient of 2. Now let me look over my grid. I've messed with the hydrogen, so now I have 2 sets of 2, which produces 4. But I've also messed with the oxygens, right? Now over here I've got 1 set of 2 and 2 sets of 1, which produces 4, right? So carbons, balanced. Hydrogens, balanced. Oxygens, not balanced, right? Where do I need more oxygens? In the reactants, right? I need more reactant oxygen. I have 2, and I need 4. How do I get 4? 2 sets of 2. 2 sets of 2 makes it 4. Now we're balanced. Now we have a balanced chemical equation. You see, I said before, generally speaking, it's true that methane and oxygen react to produce carbon dioxide and water vapor. That's generally true. But now I have a balanced reaction equation. Now I can start making some pretty bold statements, not because of who I am, but because of who God is, right? And this is the way it works. Look at, for every single methane molecule that I have, if I combust it with 2 oxygen molecules, I will produce 1 carbon dioxide molecule and 2 water vapor molecules. Pretty cool, huh? I mean, I not only know what I need and what's going to make, but I know how much I need, and if I have that much, I know how much I'm going to make. I can start predicting. And the proportions are always going to be the same. This is my perfect recipe. So, I can make the statement that 1 molecule of methane and 2 molecules of oxygen react to produce 1 molecule of carbon dioxide and 2 molecules of water vapor. I can also say 2 methane and 4 oxygens react to produce 2 carbon dioxides and 4 water vapors. Why? The proportions are all the same. I just take the coefficient and multiply it by 2. So 2 and 4 produce 2 and 4. Oh, 5 and 10 produce 5 and 10. Oh, 12 and 24 produce 12 and 24. Oh, 50 and 100 produce 50 and 100. Oh, 100 and 200 produce 100 and 200. Oh, 1,000 and 2,000 produce 1,000 and 2,000. Oh, 6.02 times 10 to the 23rd plus 12.04 times 10 to the 23rd react to produce 6.02 times 10 to the 23rd and 12.04 times 10 to the 23rd. Whatever the count is, the number count, I now know if I combine twice as many oxygens with the number of methanes, it will always produce whatever that number was of carbon dioxides and twice that number of water vapor. Always. If I have too much oxygen, what's going to happen? I'll use up enough oxygen to make these molecules, and then I'll have extra oxygen left over. Why? Because unlike a baking recipe, it's not going to use what it doesn't need. It's going to just set it aside. It's going to be a remainder. We'll get into that in more detail later. We're going to use it as a remainder. Now, only a couple minutes left. There's a reason why I used that number, 6.02 times 10 to the 23rd. That is a very, very important number in chemistry. It's called Avogadro's number. Avogadro. It sounds like avocado. For the first couple tests, if you write avocado's number, we'll see. But it's Avogadro. Avogadro's number. Avogadro. Now here's the deal. This is kind of cool. Matter of fact, this is very cool. Matter of fact, this is very important. So even if you're like, oh, there's only 2 minutes left, I can just shut down my ears and pretend like it's the middle class. No. Listen up. Avogadro's number is important. If you roll the R, you get extra credit, okay? So Avogadro. Avogadro's number is important because 6.02 times 10 to the 23rd is the number of atoms, if it's an element, or the number of molecules, if it's a compound, that are in 1 mole of that material. A mole in chemistry is not a little furry creature that pops its head up out of the dirt, right? A mole in chemistry is a unit of counting. And a mole is, well, if I said, give me a dozen, how many would you give me? 12, okay? If I told you, give me a score, how many would you give me? 20. The score is 20. So we got numbers. If I said, okay, 12 for a dozen, a baker's dozen? 13. Give me a pair. How many is that? 2. 2. Okay? If I say, give me a mole is just like, if a dozen is 12, a mole is 6.02 times 10 to the 23rd. It's a huge number, but here's the deal. Atoms and molecules are so small that if I went to you and said, hey, Ray, give me 2 molecules of sodium chloride. Like, dude, nobody can give you 2 molecules of sodium chloride. Why? It's so small, I can't even measure that. It's virtually nothing. I can't do it. But if I said, okay, give me a dust speck, you're like, well, that's doable, but it's hard. I said, okay, give me 6.02 times 10 to the 23rd dust specks. You go, my count might be off, but you know what? There's so many of them that if I hold them in my hand, I can actually see them. If I give you 2 salt molecules, you won't even know they're in your hand. They're so small. But if I give you 6.02 times 10 to the 23rd salt molecules, you can actually transfer it from one hand to the other. It's enough that we can actually start to work with it. Okay? See you tomorrow.